Today we're going to talk about strong inference, which is the method that we use in frequentist statistics to decide whether or not our data support or reject the hypotheses that we're considering. So when we're doing inference, we are generalizing. So we start with a specific thing, a sample statistic. And we might want to describe this sample with something like, what is the typical color of a dot? And once we've got this description of the sample, we can, with inference, we generalize to a description of the population that sample was drawn from. And we hope that if our sample was drawn at random from the population, that it's a representative sample. So the most typical color in our sample is probably the most typical color in our population. So we use the laws of probability to justify our generalization to make this inference about the population parameter. In order to make the laws of probability hold in the situation we're talking about, we have to be very clear about what we're talking about so that people can follow the logical steps each way and say, yep, okay, I follow that inference. And the way we do that is with a hypothesis, which is in this class, which is a statement about how two variables are related to each other and why that relationship exists. So it's going to have I see this because of this cause. And it will be stated in real world words without statistical jargon. So a hypothesis is a statement about the underlying system or process that we think is generating the patterns that we are seeing in our sample. So here are two hypotheses that we might work with in this class. One is how much material a student memorizes depends upon how long they spend studying, because memorization requires repetition. So the two variables here are the amount of material a student memorizes and how long a student is studying. And the cause and effect is that you need to repeat yourself many times before you can really memorize something. So this is a valid hypothesis. Another valid hypothesis, even though we would expect it to end up not supported by real-world data, is this one. Photographs of elephants weigh more than photographs of mice because elephants are heavier than mice. So our two variables here are, one variable is the photograph a photograph of an elephant or a photograph of a mouse? And the other variable is the weight of the photograph. And the cause-effect relationship is that we think, according to this hypothesis, that a photograph's weight will be influenced by the weight of the object that is being photographed. So once we have our hypotheses, which are not necessarily specifically tied to specific numbers, we can make a prediction, which is where we're going to tie the exact actual contents of our sample to our inference. So it's going to be a statement about the values of the sample statistics that you expect to see if your hypothesis is true. Jargon is appropriate and probably necessary. And one thing that's confusing is that what I call a prediction is sometimes what many statistics texts call a research hypothesis, because it is a pattern that you expect to see after you've run some statistics. And in my opinion, calling it a research hypothesis really confuses the issues, but even I will sometimes lapse into calling this prediction a research hypothesis. So an example would be, there will be a positive correlation between students' mean hours studied per week and their mean quiz scores. So the statistical relationship we're positing is a positive correlation, and the two concrete measures that we're taking from our sample are students' mean hours studied per week and their mean quiz score. So clearly our unit of observation here is an individual student. Another example is the average weight of printed elephant photos will be greater than the average weight of printed mouse photos. So again, our unit of observation is an individual photograph. The thing we're measuring is the weight of those photographs, and then we're going to take the average of photos that fall into the elephant group and the average weight of the photos that fall into the mouse group and compare those. So in both of those cases, our predictions laid out a logical range of outcomes that would happen if our hypothesis is true. And that means that we also can make a logical prediction about what we would see if our hypothesis is false, if the pattern that we see doesn't match our predictions. And what we call this description of the predictions that we expect to see if our hypothesis is false is a null hypothesis. It's super annoying that it's a prediction and it's called a hypothesis. I apologize for that. But it makes more sense if you keep hypothesis and prediction separate and then have a little asterisk and say, but people, when they first came up with this technique, hadn't really fully broken apart prediction and hypothesis in their minds yet. So the null hypothesis is often abbreviated as H sub 0 or H null. And the null hypotheses that go with our previous predictions are these. So for the students one, we would say the correlation between hours studied and quiz grade will be less than or equal to 0. So it's a logical opposite of what we expect to see. So any correlation that's not positive is either 0 or less than 0. So what we can see here is that the null hypothesis is completely predicted, it's completely determined by our previous prediction. Likewise, our previous prediction about photographs was that mouse photographs will weigh less than elephant photographs. So if we found that mouse photographs weighed the same, or even more than elephant photos, then that would be the logical opposite of what we expect if our hypothesis was true. So this setting up of a null hypothesis, which is what we don't expect to see if our research hypothesis is wrong, or we don't expect to see if our research hypothesis is correct, and research hypothesis, which is what we expect to see, this is the framework of strong inference that Karl Popper set up. Karl Popper is unique in this class because he's the one statistician that we'll talk about who wasn't a complete racist asshole, which is great. So we can extrapolate, we can make inferences if our data make it seem reasonable to reject the null hypothesis. So this is the origin of the expression you may have heard, is that science doesn't prove hypotheses, it only rejects hypotheses. This is Karl Popper's idea, that if you set up the null hypothesis, and if you can prove the null hypothesis sucks, then that is evidence that your research hypothesis, which is the only thing that's left after your null hypothesis has been thrown out, if the null hypothesis is gone, then we only have the research hypothesis to work with. So once we reject the null hypothesis, we can say that our research hypothesis has been supported. And that is strong inference.